This video is on complements of sets. When we're thinking about a set, we're usually thinking of it as a subset of some larger universal set. So for example, the prime numbers are natural numbers that have exactly two distinct divisors, 1 and themselves. So if we let P be the set of prime numbers, before we think about that universal set, let's just ask ourselves, is 1 an element of the prime numbers? Is 5 an element of the prime numbers? And is 4 an element of the prime numbers? So is 4 an element of the prime numbers? No. It has more than two distinct divisors. So 1, 2, and 4 are distinct divisors. So it does not have exactly two distinct divisors. And so that means that 4 is not an element of the prime numbers. Is 5 an element of the prime numbers? Yes, because 1 and 5 are the only divisors of 5, so it has just two distinct divisors, and therefore 5 is an element of the prime numbers. Is 1 an element of the prime numbers? This is no, and it's no because 1 has only one distinct, in mathematics distinct means different, has only one distinct divisor itself. And so 1 is not an element of the prime numbers. But when we are asking questions like this, we would just usually say other natural numbers. So we wouldn't normally say, is star an element of the prime numbers, or is truck an element of the prime numbers, or even is 1.684 an element of the prime numbers. I mean, these are all questions we could ask, and the answers to each of those questions is no. But typically when you say, what's a prime number? Is this prime? Is 37 prime? Is 45 prime? Etc. Usually we're really thinking of this universal set that's sort of understood for the prime numbers. And in the case of the prime numbers, the set of natural numbers is that universal set. So P is a subset of the natural numbers. Those are those counting numbers, 1, 2, 3, etc. P is a subset of the natural numbers, and we think of the natural numbers as being the universal set for P. How about the set of even numbers? What is the universal set for them? Well, even numbers are things of the form 2 times n, such that n is an integer. And so Z is the universal set for the even numbers. So the set of all integers, that's the set of positive and negative whole numbers, as well as 0. That would be our natural universal set for the set of even numbers or even integers. So if A is a set, then the universal set is typically denoted by a capital U. So if A is a set with universal set U, then the complement of A is the set A complement. So we will denote it with a line over top to denote A complement. It's the set U minus A, or the difference of U and A, where, or that could also be explained as the elements of U of the universal set such that X is not an element of A. This can also be denoted as A with a C or A prime. Those are all ways to denote A complement, but we'll denote it with a bar on top of the set. So as an example, the complement of the set of prime numbers is also a set, and that set would be the following: all natural numbers that are not prime numbers, 1, 4, 6, 8, etc. If we talk about the set of even integers, then this is the set of even integers that we've mentioned, multiples of 2 times n, where n is an element of the integers. The complement of that then would be all integers that are not even. That ends up being the odd integers is the complement of the even integers. So we could write it as 2n plus 1, such that n is an element of the integers. We can certainly think about complements of things that are not necessarily numbers. So if A is all the different ways that we could roll doubles in two die rolls, to roll 2 1s or 2 2s or 2 3s or whatever, then A complement would be all the ways that we could roll two different numbers in two die rolls. So in the examples above, there was sort of a natural or assumed universal set. Sometimes the universal set is specifically defined. So here's an example like that. Let's just let A be the set 1, 2, and 5, B be the set 1, 5, 7, 8, and 9. And we are defining that both of those have the universal set U being integers between 1 and 9 inclusive. So given that, find A complement, find B complement, and find A union B complement just as quick practice. So pause and find those values quickly, or those sets quickly. Okay, so A complement, that's every value or every element that is in the universal set but not in A. So the elements of the universal set are the integers 1 through 9. But 1 is also in A, 2 is also in A, so A complement would be 3, 4, 5 is in A, 6, 7, 8, and 9. B complement would be all the elements that are in the universal set but not in B. So 1 is not one of those, but 2, 3, 4, 6, 7, 8, 9, that's it. Okay. And A union B complement, so there we could one way we could do that is to first find A union B. So A union B is 1, 2, 5, 7, 8, and 9, and then complement that set. And so all elements that are in the universal set but not in A union B complement, let's see, 3, 4, and 6 are the only elements that are not in A or B. So great. So here's one more set of problems to look at. So here we've got a new set A and a new set B defined, as well as a new universal set. So I'd like you to, again, pause and try these out. Grab a piece of paper, find each of these sets. Okay, so A intersect B complement. So let's first find what's under the complement. So let's find A intersect B. A intersect B. E is the only element that is in both A and B. So now when we complement that set, we get the set of all elements of the universal set except for E. So that is A intersect B complement. A union B complement, again, we'll find A union B first. A, B, C, D, E. And then we will complement that set. So this is what is in the universal set but not in that. The only element that is in the complement would be F. So it's just the set containing F. How about A complement intersected with B complement? So that would be A complement is B, C, D, F intersected with, that is A complement, intersected with B complement, intersected with, B complement is A, B is not in there, C, D, E, so A and F is B complement. When we intersect those two sets, the only element in both of those two sets is the element F. Now we'll find A complement union B complement. So again, we can find A complement first. A complement everything that's in the universal set but not A. That would be B, C, D, and F. And B complement would be A, B, C, D, E, F. So the elements that are in the union of those two sets would be A, B, C, D, and F. So something to notice right now is that A intersected with B complement is equal to A complement unioned with B complement. And we can also notice that A union with B complement is equal to A complement intersected with B complement. So that was true in these two particular cases. Later we'll show that that is always true when we do proofs about sets. So our next ones, here I'm just copying down those sets again, just so that we have them in the same screen. What is A complement complement? So that is, first of all, we do the complement of A, and then we take the complement of that set. So the complement of A, as we've seen above, B, C, D, F is the complement of A. Then we want to take the complement of that. And what do we get? Everything that's in the universal set, but not in the complement of A. So that would be A, B, C, D are in there, F is in there, A and E. And, oh, that happens to be A again. So the complement of a set is the set of its set itself, and that is always true as well. That the complement of the complement gives you the original set back for any set. A Cartesian product with B complement. So this would be A, E, Cartesian product with the complement of B, A and F. So that would give us the set of ordered pairs A, F, E, A, and E, F. That would be the Cartesian product of those two sets. B intersected with B complement. So everything that is both in B and not in B. So are there any elements that are both in B and in its complement and not in B? No, there are no such elements. That would be the empty set. And what is the power set of B complement? So that's the power set of B complement would be power set of the set A and F. And that would give us the set of subsets. So the empty set is a subset, the set containing only A is a subset, the set containing only F is a subset, and the set A, F is a subset as well. So here's one last problem I'd like you to try to find if C is the Cartesian product of the closed interval 1, 3 with the open interval from -1 to +1, then sketch C complement. And as usual, we assume that such a Cartesian product is a subset of the reals cross the reals, or in other words, the XY plane. So pause, sketch that set, and we'll look at it. All right, so we're sketching the complement of this set. C is the Cartesian product of the closed interval from 1 to 3 with the open interval from -1 to +1. Since we're outside the closed interval from 1 to 3, we could draw that as a dotted line because we don't want to include those endpoints. And we're outside the open interval on the y-axis from 1 to -1. So we're outside of this here, so that's all included, and everything out here is included as well. Everything out this way is included, basically everything that is not inside that partially open, partially closed rectangle C. So here is C, and C complement is everything outside of that. Again, I've drawn dotted lines vertically because the actual points here are not included in C complement. They are actually in C, whereas I've drawn solid lines here that are horizontal because those points are in C complement. They are not in C.